yeah, so I'm going to talk about these tools, VirtualizZarr and IceChunk, and this sort of tongue-in-cheek goal of building an entire cloud-optimized DataCube in just 3 lines of code. So about me, I am a forward engineer at Earthmover as of a couple of months ago, but I have a background in physics and then pivoted to climate science and geoscience data. And so I have this kind of multidisciplinary background. So I work, plasma physics, oceanography, and I got the link between them was the domain agnostic open source tools like Xarray and Zarr. So I'm an Xarray core developer along with Joe and Deepak here. And I work on various other projects in Pangeo, and then this VirtualizZarr thing is like the first Zarr-related project I've worked on. I work at Earthmover, this cloud data company, one of the sponsors of the conference, cloud data platform for scientific data teams, and we're a public benefit company, public benefit corporation, with a mission statement to empower people to use scientific data to solve humanity's greatest challenges. So this talk is the result of a story that started before I worked at Earthmover. So 18 months ago, I was basically asked, I was working kind of as a data engineer for the first time rather than as a developer, and I was asked to cloud optimize some data. I've only just finished that task, and I don't even work there anymore. But the talk is because doing that task was so much harder, cloud optimizing this data was so much harder than it should have been, that I ended up writing a new package to make it easier. And now I think I can get the job done in 3 lines of Python. And I want to argue that this approach, this VirtualizZarr package in an IceChunk format, should work for basically any level 3 or 4 data set. It also has the huge advantage of avoiding copying the original data. So it's really like a cloud-native bridge for archival data. And a lot of people were involved, various other contributors to VirtualizZarr, including a bunch of people who were at the conference, especially, so all of these people are at the conference. And various organizations. I'm also going to show off this map thing that I was involved in making, but really some other people did the hard part. So what are the 3 lines of code? So roughly 3, we're going to explain these in depth, but we're creating references to chunks in the files, combining them. Line 2, we write them into a persistent format, and line 3, we make an immutable commit. So what was the data set that caused me such a headache? So it's something called the Seaworthy OAE Efficiency Atlas, which is basically a massive ensemble of climate model simulations. I'd say they're arranged in a grid. You might call them tiles. It sits on S3 on source cooperatives, a bucket provided by source cooperative. This is an S3 bucket, a lot of NetCDF files. But the NetCDF, which is annoying, it's 50 terabytes of data, something like 200 terabytes uncompressed, so it's quite big. 500,000 NetCDF files, that's quite a lot of files. And logically, it's a 6-dimensional data cube. So we had a whole talk about data cubes in an earlier session from my co-workers, Lindsay and Deepak. But this one has 3 spatial dimensions, 1 time dimension, 2 ensemble dimensions. And it's like genuinely a 6-dimensional data cube, like a dense one. So after much data wrangling and partnering with these visualization experts at Carbon Plan, including Shane, who's here at the conference, then a beautiful visualization was made in which you can select a simulation and show the propagation of this stuff that you've dropped into the ocean, which is all really very nice. But the way that I actually got the data, the way that I was given the data, was much uglier. It was a pile of files or tiles in a bucket with no easy way to read the structure. And this is very common because, unfortunately, this is what passes for a cloud data archive in a lot of cases when people share data and they say they're using the cloud. But it's really the result of just like naively lifting non-cloud optimized data into a bucket. But what this is missing is the fact that like it's not really a jumbled pile of files. It's a grid or a tile set of tiles which have structure between them. And so in my case, it was a bunch of NetCDF files, but it could also be a bunch of TIFF files, whatever. It's the same kind of high-level structure. The real problem here is that the data formats are not cloud optimized, which means that any client code trying to read this massive data set, to even know what's in there, has to start by looking at the metadata spread throughout the files, and then do this for every single file, and check all of the files can be combined into a logical data cube, which takes even longer than my little animation there. And if you called something like Xarray open MF dataset, standard multi-file dataset, then that's what it would do. It would naively loop through all of the files to learn what was in there so that it could be confident that the whole thing was a DataCube. If you read my recent blog post, then you would know that actually the situation is even worse than this, because it also takes a really long time just to read the metadata from one file, because it's a non-cloud optimized format. And that's basically because the metadata is spread throughout the whole file, and getting it with individual GET requests is really inefficient. So that means it can take like a minute per file, and we have 500,000 files, which adds up to literally a year if you don't parallelize the opening of this. And you have to do this every single time you try to access the data set, even though you know a priori that it's a DataCube. I don't have time for that. So the conventional solution to this problem, at least in my field, is to rewrite the data as Zarr. So you take all your NetCDF files, you copy, paste them into Zarr. This works great in the sense that now, because Zarr has consolidated metadata at like the top level, and you just fetch that one bit of metadata, and now you know, you're confident that the whole thing is DataCube, then now the time to open it has been reduced from a year to a second. But there is a disadvantage of this approach, which is that we've doubled the storage, because we still have the NetCDF. Like, quite often there's a requirement to keep the NetCDF files around for some reason, especially in like public agencies. And so if we duplicate a Zarr, we've got 2 copies of the data, which uses twice as much space and means that they can become inconsistent with one another. But what if instead we just made the NetCDF somehow look like they were Zarr, so that client code could read them as efficiently as Zarr, but they were actually still NetCDFs underneath? In other words, we need some kind of layer on top of the NetCDFs to disguise them as something else. That layer is IceChunk. IceChunk, and particularly IceChunk's ability to store what are called virtual chunks. IceChunk is really cool. It's a open source software from Earthmover and a file format. It's really technically a transactional cloud native storage engine for Zarr. It's really like a serverless OLAP database. It works together with Zarr Python 3 and Xarray. So if you have code that reads Zarr, your code can read IceChunk. And so the Xarray community can just immediately adopt IceChunk. And for this presentation, the crucial thing is it supports this concept of virtual chunks, which I'll explain in a minute. IceChunk is also, it's implemented in Rust, so it's super fast. And we can make bindings for other languages, and it's open source. You should have a look, because it's very cool. So what does VirtualizZarr do, the other half of this? VirtualizZarr extracts the virtual chunks. So if you import the VirtualizZarr library, you call this open virtual dataset function on, for example, a NetCDF file, but it could be some other type of file, a non-cloud optimized file. You get back this virtual, quote-unquote, Xarray dataset object, which contains, under a couple of layers, it contains these chunk manifests. And these are basically mappings from Zarr keys to locations in storage, like S3 URL, and then the locations, like byte ranges within the file. And combine it, so you get a bunch of those for one file, and then you want to combine them all together to make your DataCube. But you really are talking about a grid of chunks. And so so the problem of combining all the chunks together is itself an array concatenation problem, which means we can reuse Xarray to do it with a bit of cleverness. So that's what VirtualizZarr does. It allows you to use the Xarray API that lots of people are familiar with. It's got nice primitives for concatenation and merging to combine lots and lots of files together. And then finally, once you've made your set of references that spell out your whole DataCube, you can write them into an IceChunk store, or VirtualizZarr can also write to the chunk format as well. So that's how we're going to do it, but we still got to scale to 500,000 files. So we've got to run open virtual dataset on every file, and then combine them back together. And Xarray already has a primitive called openmfdataset that does basically the same thing. So we're going to use that as our API on just the list or the glob of all the file paths. And we're going to serverlessly map that function using AWS Lambdas, because this is basically a map reduce problem. So here are all my Lambda functions spinning up. Each one runs one open virtual dataset call on one NetCDF file or one other type of file. And then they all produce these little chunk references, which are millions of times smaller than the actual chunks, come back to that, which means you can send them all back to the coordination node or whatever where the concatenation operation is performed. And because these are so small, you can actually just send them back to your laptop, and it works fine. And then once you've got that thing all aggregated together, you can write the references into IceChunk. And so you could run like one Lambda for every single file in theory, but AWS for like normie accounts only lets you have 1,000 Lambdas at once, and so I might as well batch them in something like 1,000 each time. So the demo it's a little janky, but it's basically 3 lines. Like you open everything here and combine it, you write it into IceChunk and it comes out. And what you just saw there was in 20 seconds, we had 720 files processed. And then I'm running this in a loop, so it's going to do another 720 and so on. And so what this means is that I'm able to just like from my laptop, run these on Lambdas, ingest this data. Overall, it ends up being about 10 gigabytes. It's the equivalent of like ingesting 10 gigabytes of data a second. But we could make it quite a lot faster. And if we did it with 500,000 Lambda functions at once, maybe if I asked Jed nicely to like hook me up with someone who can raise my limit on my account, then we could get the whole thing done in like less than a minute from your laptop. The loop shows that you can do this for batch. So if you have data coming in over and over, you can just like commit like an immutable version of the data and then like get more references and then commit a new version of the data, which is where IceChunk is really useful, something that a chunk format cannot do. Or normal Zarr can't do that. It also means it's resumable, so if this were to go wrong, I can just keep going from where I left off. And it's a very general paradigm, like we're just concatenating these like arbitrary multidimensional arrays. And it's roughly 3 lines of code, conceptually. A little bit of polishing needs to be done here. I was hoping to release this before the conference, but you might have to wait a week or two. And the scaling demo shows like what is possible here. But VirtualizZarr and IceChunk work together today, and so if you want to learn more about that, you should come to the workshop that we're running, Earthmover workshop, where we've got a little section on that. And this approach to cloud optimizing data is like a lot simpler than any other approach I know of to cloud optimized data. And note that at the moment, VirtualizZarr supports like HDF5 and a couple of other formats, but the other thing we were hoping to get out for this conference was TIFF support. There's some people working on JPEG support. We want GRIB support as well. In general, you could do this for basically any file format where you can read from it as like contiguous HTTP range requests, which is how it links back to what Howard was doing, because I'm pretty sure that his point cloud format is also like within that set of formats. But if you want to know more about the gory details of like what's actually going on there, you should probably talk to Sean Harkins, who is also at the conference. So in summary, level 4 data, 3 or 4 data sets are often in archival formats, but really should be in Zarr because they kind of have a Zarr-like structure. It's almost as if like everything is really just an array, including vector data, like Emma said. And so I kind of think that this is like why IceChunk is extremely powerful, is that like you can just think of many, many things as an array and put them all into one transactional serverless database. The virtual feature of the IceChunk stores means you can point at original files without copying the data. VirtualizZarr allows you to build virtual data cubes at scale using the Xarray syntax that people are already familiar with. And then IceChunk's sort of atomic commits allows you incremental updates as new data arrives. And so overall, you can kind of like compare different file like distribution options, and IceChunk is just basically better in every respect, in my opinion. So yeah, that's my talk. Thank you.
We have questions. Yes.
Thanks, Tom. That was really cool. I actually don't know the answer to this question. I mean, we used to work together, so it almost seems like I might, but I really don't. In the like very minimal 3-line version of this, where is the commit history of your IceChunk store? If you're resuming this like across Python sessions, where is your commit history stored? And how does that evolve over time if you have a more production grade system?
Good question. So IceChunk is deliberately a bit like Git in that it has commits, it has tags, it has branches. In this case, I am just using the default of basically like opening the most recent version of the main branch. But you could open a specific commit, open a specific tag, make a new branch, do all of those things, and then write to any one of those. In this case, I'm just glossing over that because I'm kind of assuming that you just want to continuously append to like your sort of main branch, but you can do all of that.
And so sorry, just to clarify, that revision history is stored on object storage as JSON or SQLite or?
It's stored as a series of like IceChunk native tiny files purely on S3. There's no other like database running. And then when a new commit is added, IceChunk does like an atomic put if not absent call to S3 to like swap a little new file, which allows like multi-tenant reading from the store. So that's how they're recorded as little files alongside the actual chunk files.
Gotcha.
Yeah.
Thank you. That's helpful. Thanks.
You have a question? No. Okay.
Thanks. Hey, yeah, super cool. I'm wondering, it looks like this was developed in order to take an entire data set that was not cloud optimized and make it cloud optimized. I assume you could use the same tools, but I'm wondering if there's any benefit for essentially creating like a new real-time archive of some type of data. That's, for instance, weather forecast data, right? You get new files in all the time, want to add them to the thing. Are these tools beneficial for that, or yeah, maybe you kind of know what I'm asking.
Good question. I think the answer is yes. And what it comes down to is that there's the concept of cloud optimizing an individual file, which can be done with like cloud optimized HDF, like cloud optimized GeoTIFF, like representing that one file as Zarr. And then there's the separate problem of having some immediately accessible way to say that these billions of files are all one DataCube. And so even if your files were already in like a cloud optimized format, you won't necessarily, it doesn't mean you have that like DataCube, that single URL that allows you to refer to the entire logical data set. And that's when it can be useful with this kind of ingestion thing, where maybe like you're getting cloud optimized files from your weather forecasts or whatever, but like you want some way to present them all to the user as part of one massive cube. And then VirtualizZarr is useful for that, even though the data is already technically like cloud optimized on a per file basis.
It's not, it's coming in as grids.
Okay. Yeah, we want to put grid support for VirtualizZarr as well, because grids suck.
But, okay, so that does work, right, to continue. Oh, sorry. So that does work then to, even if it's a non-cloud optimized file coming in, it will, it is the right tool for the job of building the archival set that is then accessible by a client or
that's
or
exactly
interested
what
party.
the motivation was, yeah. Yeah.
Cool. Thanks.
Yes.
See, potentially similar. I'm working with some hyperspectral data. There's 300 plus bands. Do you see any? Which is almost impossible to work with in my current conditions. Is there any? Do you think your toolkit or toolset could help make things more efficient, computations, things like that? I've never worked with IceChunk before, so I wasn't quite sure at all. So I figured I would ask.
That's a little light on detail, but the problem with the bands is that you have a very large number of variables. Is that the issue?
Yeah, just the overall, I guess, not necessarily a DataCube, but just the computations are so slow and almost impossible to do basic things with. I'm trying to branch out to find things that work with it, and it's kind of in the exploratory stages of it at the moment.
I mean, Zarr and IceChunk are designed from the ground up for scalability on object storage, and you can achieve you can basically max out your like network connection within the cloud using the IceChunk Rush reader because it's so efficient. So it's like approaching the limits of like how fast it is physically possible to even read the data. So I think that's quite good. Exactly. Yeah, it makes full use of your fat pipe. Exactly.
Yeah, thanks for the great overview. One of your later slides, you just had a passing reference to Kerchunk, and I'm just wondering, how does the IceChunk
Yeah.
relate, and how is it different?
Yeah. So I obviously anticipated this question. Here's a
Yeah.
bonus slide. I originally tried to. Xarray is two things. Xarray is a Python package, and I made VirtualizZarr to replace that Python package. Xarray is also a format for storing chunk references, and IceChunk is an alternative to that, which adds the kind of transactionalness. So you can use VirtualizZarr was actually conceived before IceChunk was released, and so VirtualizZarr can write to the Xarray format, but if I were you, I would write to the IceChunk format, because then you get all the other benefits of the transactionalness and the update safety and so on. Yeah, and I don't really see a reason to continue using the Xarray Python package, because I think VirtualizZarr does basically all the same things, but is easier to use.
All right, thanks.